This trig equation is not easy to solve. I mean, take a look at the coefficients in front of the x's. They're huge. What am I going to do with tangent of 13x? Expand this in terms of tangent x? No chance. This is going to take forever. Maybe I can expand sine of 2x, but tangent of 13x, definitely no chance. So we need a more clever method to solve this equation. I invite you to pause and ponder on the structure of this equation. What makes this equation convenient to work with? You might notice that tangent has an input of 13x, and cotangent, which is just the reciprocal of tangent, it also has an input of 13x. So maybe let's put cotangent of x, or cotangent of 13x, onto the other side. Let's move this over onto the other side. And also, let's move this sine of 2x onto the other side as well. You might be confused as to why we're doing this and what the motivation is, but I'll tell you why this is so powerful in a moment. So let's get moving. Let's rearrange this to tangent of 13x, and then plus cotangent of 13x. This is equal to cosine of 8x, and then plus sine of 2x. Now, why is this so powerful? Well, I want you to observe this side. This expression is key because notice that cosine and sine, they are both bounded. These two functions both have a maximum value of 1 and a minimum value of -1. So there's a clear bound to the value that this expression can become. However, if you pay attention to this side, well, this looks very much unbounded. I mean, I can make this 1 million if I wanted to. Because tangent and cotangent, they can grow as much as they like. So it seems like this side is unbounded in that sense. However, have you ever thought about this? Is there a value that this expression must always be greater or equal to? Okay, so I've decided to write the cotangent as 1 over tangent. Now, consider this. We have an expression that looks like something plus its reciprocal, and we want to determine a bound for it. Well, whenever you see something like this, it's usually a good idea to consider the AMGM inequality. Now, in case you are not aware of what the AMGM inequality is, I will briefly explain it here. So, I'm going to explain the AMGM inequality. It states that if you have non-negative real numbers a and b, then it follows that the arithmetic mean of the two numbers is greater or equal to the geometric mean of the two numbers. That is what AMGM states. Now, you're probably familiar with this. This is just your usual average, so a plus b over 2. But this over here is something called the geometric mean. So you can probably imagine how the name is derived. This is AM, arithmetic mean, is always greater or equal to GM, the geometric mean. And furthermore, if these two are ever equal, then you must conclude that A is equal to B. And it also works the other way around. If A is equal to B, then these two are equal. So this is the AMGM inequality. So I'm going to write this as the equality condition. Equality if you have A is equal to B. And it's actually an if and only if statement, meaning that you can only have equality if these two are equal, no other cases. Okay, so now that we've got to the AMGM inequality, let's use it. Well, consider this. This side, by AMGM, we have that tangent of 13x plus 1 over tangent of 13x. This divided by 2 is always greater or equal to the geometric mean of this times this. They cancel out. It's just 1. That's why it's so convenient when you have something plus its reciprocal. The GM just becomes a constant. And now you can multiply both sides by 2, yielding that this plus this is always greater or equal to 2. In fact, let me just shift this upwards. So this is always greater or equal to 2. Beautiful. Okay, so because this is equal to this, we must conclude that this thing is always greater or equal to 2 as well. But do you see what's going on? We have a cosine expression plus sine expression is greater or equal to 2. But the maximum value of cosine and sine are both 1, so the maximum value of this is 2. So if it's always going to be smaller or equal to 2, and at the same time greater or equal to 2, the only possible option is that this is equal to 2, right? Okay, so we derived this equation. Now, notice that we have a cosine expression plus sine expression to be equal to 2. And we know that the maximum values of cosine and sine are both 1. Well, if you want these two to add up to 2, then the only possible way for that to happen is if both of these are equal to their maximum values, or 1. So we can actually derive that cosine of 8x has to be equal to 1, and sine of 2x must also equal to 1 for this equation to be satisfied. Now, this is much simpler. We just need to find all values of x such that both of these will be satisfied. Now, it might be tempting to do something like this. We can take a look at this equation and go like, oh, 8x is equal to 2k pi for any integer k, and over here we have 2x is equal to something, and then try to find overlap solutions. But that can be kind of complicated, and even if you do find some solutions, you're going to have to deal with the period of cotangent and tangent later on in the original equation. So as of right now, let's just try to be simple. Let's just find the least positive value of x, such that both of these will be satisfied. And if you do some inspection, you'll see that the least possible positive value of x would be equal to pi over 4. So this is our answer, right? Well, not so fast. Notice that we got this value from an inequality. We used AMGM to derive a bound of this expression in order to finally arrive at this value. But inequalities do not guarantee that this value will satisfy the original equation. So we're going to actually have to plug this into the original equation to check if it actually is a solution. And I'm going to leave it to you. You can actually plug it in and you'll see that it is a solution. Okay, so now that we have that down, let's find all possible values of x. Because remember, these are trig functions. They are periodic, so they'll most likely allow for more solutions, infinitely many, most likely. So we're going to have to deal with that. Well, to start off, we could maybe observe the period for each trig function in this equation. So for example, over here, this tangent function has a period of pi, but then we have a 13 over here, so it's pi over 13. And over here, sine has a period of 2 pi, but then we have a 2, so the period is just pi. And we have cosine 8x. Well, cosine has a period of 2 pi, but then we have 8. So we divide that by 8, giving us pi over 4. And over here, well, that's the same as tangent. This would be pi over 13. What we actually seek is the least common multiple of all of these periods, right? And clearly pi is the greatest one over here, right? Okay, I circled. I'm so sorry. But you can see that pi is the greatest period among all of these. And pi is also an integer multiple of all of these other periods. So it is the least common multiple of all of these periods. So this trig equation has a period of pi. So therefore, all of our solutions can come in the form x is equal to pi over 4 plus k pi, where k is an integer. And we're done, right? Not so fast. Notice that originally we assumed that both of these were positive in order to use AMGM, right? Well, what if both of these were negative? Yeah, what happens, right? We have not dealt with that case. So we have to deal with that case in order to conclude that this is our, well, we have to deal with that case in order to find all possible solutions or to conclude that these are the only ones. Now, to be honest, the argument for when both of these are negative really is not that different. Notice that when both of these were positive, we were able to derive that their sum would be greater or equal to 2. But then, if both of these are negative, then what would that imply? Well, imagine the number line, okay? And just think about reflecting some number across 0 on the number line. That's what happens when you make the terms negative, right? When both of these are negative, you're basically reflecting the value across 0 in the number line. So therefore, if both of these were negative, then we would conclude that their sum would be smaller or equal to -2, right? And because this is equal to this, we must conclude that this expression is going to be smaller or equal to -2. But at the same time, we know that cosine and sine both have a minimum value of -1. So this would mean that this expression is always greater or equal to -2 at the same time. Well, these two would squeeze out the fact that cosine of 8x plus sine of 2x is equal to -2, right? And similarly as before, from this we can derive that cosine of 8x has to be equal to -1, and sine of 2x would be equal to -1. Now, if you try to find a value of x such that both of these are satisfied, you'd be here forever. And that's because there are no solutions. How do we prove that though? Well, the way we prove it is kind of the most straightforward method. From this equation, we get that 8x must be equal to, well, it's equal to -1. So 8x is equal to pi plus 2k pi for any integer k. And from this sine expression, the sine equation, we get that 2x is equal to, it's equal to -1 again. So this would mean that 2x is equal to pi over 2, and not pi over 2, what? It would be equal to 3 pi over 2, and then plus 2n pi, where n is also some integer. Now, notice this. We can multiply both sides of this equation by 4. So this would be 8x is equal to this times 4, right? And because both of these are equal to 8x, right, we can set these two expressions to be equal to each other. So setting them equal to each other, we get that pi plus 2k pi is equal to, let's just distribute the 4 in, that would be 6 pi plus 8n pi. And we can divide both sides by pi, so we have, do you see the contradiction here? We see that this side is surely even, but this side is surely odd. Clearly, odd cannot equal to even, so we have a contradiction. So therefore, this is not possible. Now that we've considered all possible cases, we can indeed conclude that this is our only possible solution. Now, I hope this problem has taught you some problem-solving skills. For one, notice that when you're dealing with trig equations, when the equation looks very complicated, it's usually a good idea to think about bounding arguments. And it turns out that bounding arguments are super helpful when dealing with trig expressions because they help you squeeze out certain possible values that some expression must be equal to. Anyways, I hope you found this video enjoyable. I hope you found it interesting. If you did, then please consider dropping a like and subscribing. Thank you very much. Bye.